or uncertainty. That is, as I understand it, the contributions of calibration to this variability we see in all multimodal studies, either due to the fact that people are using different models or that different groups are using the same one. So, yes, I think we're going to start now and stop. Well, and on the first point.
Okay, well, we thought, as this is a working session and it's not entirely clear what a working session outcome is supposed to be, we thought that the focus is mostly on community building. So what we would want to do is do a quick round of introduction of all of us, and we're not too many. So you say your name, where you're from, and what your core interest in calibration or uncertainty is. And then we have a small online file with just like 3 questions. You see the URL there. It's short so that you can copy it into your phone or computer if you want to participate. If you don't want to do that, we can also skip it. But that was like basically a warm-up idea. It's not essential. So yeah, I'm Christoph Gunnar. I work at the Potsdam Institute for Climate Impact Research with a global crop model, which actually is a global biosphere model, and crop systems are just one of the systems. And I've just spent 2 months times 10,000 and not times 1,500 CPUs on calibrating that model, and it did work. So I'm interested in how to make calibration work well, and I guess we all need some level of calibration.
Hi, this is Shuaqiu. So I'm from UC Davis. So I'm working on making a process-based model called AgMIP10, published by FAO. I'm trying to make it a gradient version of Python, and I'm also interested in like calibrating it and evaluating it. I mean, following the calibration protocol of the AgMIP. Thanks.
I want to talk about
Hello, I'm Hamza from Morocco. So I'm working with I've seen the stat model, but we have all the time a big problem about data, and especially how we can calibrate the model. Even we can use, for example, some results from machine learning or remote sensing, and we can use it as calibration with the model. Because at all time we can just count, for example, yield or almost yield or a little bit some data of biomass. So all time, for example, even we have the data for a model for simulation, but we have a big problem about calibration.
Yeah, Pierre from INRAE, Montpellier. So I'm mostly interested in area of calibration to calibrate models for large numbers of genotypes and linking with phenotyping. So having a mix of parameter estimating from phenotyping and mixed of parameter estimated from state variables measured.
Yeah, hello, this is Jan from Delft, Germany. And my interest is on applying some protocols developed by Daniel's group to our simplest models. And one of the reasons is just to reduce the uncertainty due to the prime modelers, but also our group is focusing on making this calibration things more reproducible across our colleagues. So we want some standard calibration protocol for our group.
Hello, my name is Aston Chibanshi, and I'm from Saskatchewan, Canada. I've been working on a number of crops, and I used DSAT for lentils and peas. I've now branched into working on potatoes. I've been making measurements of phenology, leaf area index, and agrometeorological observations in a potato field. This is now second year of data collection. So I'm wanting to find out. I couldn't find a model really for potatoes, so I'm really wanting to see if I could come up with a calibrated model for potatoes so that we can start simulating the potatoes as well.
Hello, my name is Jens Hanesiadis. I'm a chair of AI at Wageningen University and Research. And my interest is in how we can use machine learning for calibrating crop models.
Georg from the Center of Agricultural Landscape Research at the University of Bonn. I have a general interest in crop modeling, calibration, crop model calibration, and perhaps more specifically on the minimum requirements, data requirements for calibration, perhaps also in comparison to validation. Thank you.
Hi, my name is Raniero della Peruta. I work at the Euro-Mediterranean Center for Climate Change, CMCC, and I'm currently working with a model for coffee. And I'm interested in how to calibrate and how to estimate uncertainty in areas with low data, basically. So in other projects, we have instead data sets with more comprehensive data, but still the calibration of a model with hundreds of parameters is really something that requires good ideas. So thank you if you give us good ideas to do that.
Michael, the Hebrew University of Jerusalem. I'm interested in how to calibrate models from commercial field in Argentina that don't have a lot of science data, the yield, and only basic data.
Ben Jones, Field Applied Research in Australia, working on improving APSIM next-gen wheat at high yields and involved with measuring things and quite acutely aware of the uncertainty in those numbers as well, and so interested in trying to manage that and identify it in model development.
Hi everyone, my name is Sabar Khabar. I'm from Egypt and I'm interested in the calculation of the crop models, how to calculate the crop model or have better calculation with minimum data sets or small data sets. I used to work with data at AquaCrop and APSIM, and currently I'm more interested in joining or integrating crop model processing process models with the other data analysis tools like machine learning and machine vision. Thanks.
Hello, my name is Moses Almeron. I'm at the University of Kentucky. I'm interested in maybe opportunities to collaborate between the AgMIP soybean team and the calibration team. And then at a personal level, from my lab, I'm also interested in calibration tools, particularly for in-season data.
Hello, my name is Samuel Buy. I'm from INRAE, France, working on development of methods and software for parameter estimation and sensitivity analysis. And I'm co-leading the team which is developing the STIX crop model and part also of the co-leaders of this calibration initiative.
Hi, my name is Vidor. I'm from the University of Hamburg. I work with the GTCMI model output, and I'm interested in learning more about how these models are calibrated and foster the uncertainty.
Hello, my name is Xinxin, and I'm based in Love. So I work with Jiang about the calibration of simplex, and I work with Pierre about using their quality to do some calibration work.
Hi, I'm Lennart Jansen from the PIC, and I'm interested in modular uncertainty and the fine line between calibrating to represent better physical processes and calibrating just to get a good fit.
Hello, my name is Thomas Oberleitner from IDASA. I also only work with model outputs, but I'm interested in model uncertainty and using machine learning or general optimization algorithms to calibrate models. Yeah.
Your turn and my turn.
I can continue with. So I see many people not having a digital tool, which is good in general. And if anyone tried that URL, I tried and I couldn't fill in anything. I'm not sure. Like we were inspired by you, Yanis, yesterday in your session, and we will follow your role model in skipping this and doing it. Sorry for that. Sorry for making you include a useless URL. But so maybe just to do a show of hands, who in the room would say, I like calibration to an extent that I would wear a t-shirt that says, I like calibration. Daniel said he was the only person in the world, and I just wanted to prove him wrong.
There, I don't believe them.
Okay, who would also say that calibration is a nuisance and it's pain in the neck? Okay, that's a little bit more than people liking it, and there's some overlap, so that's fine.
But I think the question should be, who has actually tried to do calibration and finds that it, maybe the people who didn't say that it's a pain in the neck are the ones who haven't done any calibration.
Okay, whoever had a pleasant calibration experience. Okay, there's people, you know. Some people like suffering too, right? Okay, maybe.
How about the people that are worried that calibration is distracting them from the other things that are wrong in the model?
You get that.
People who think that calibration is distracting them from things that are wrong about their model. Oh,
calibration as a distraction from addressing real problems.
Yeah.
Good. Who would say the human factor in overall uncertainty? Okay. Is less no. Who would say the human factor in overall modeling is more than 50% than total in total uncertainty?
1 second.
What's
What's
your sample?
But everyone has their own sample, and like from your experience, would you say 50% of uncertainty is at least caused by the humans in their calibration, in the setup, in the selection of the model, in the selection of the research question?
But in building of the model.
All include. I mean,
And obviously all models are built by humans, so yes.
100%. Okay, that's good. Let me see what else I have here. Would say crop yields is the main target of the calibration, like the most useful target in the calibration.
Most useful or main target?
But if you do a calibration, do you do it to get yields right?
Eventually.
Oh,
But also.
Yes.
Yeah.
Sometimes. So that like who at least includes yield as one of the targets in the calibration. It's like 100% good. Then you're elected. And who would include in the calibration within season indicators? If you have them, of course, yes. And who would include in the calibration any environmental impact of the cropping system, like leaching or greenhouse gas emissions?
You generalize that to model behavior. Did you generalize that to model behavior within a season? Like we've lost in response to treatment factors. That's sort of what you're looking for again.
Yeah, I mean, this is not a very scientific. Sorry, but just trying to get a sense of what people are doing in the calibration. And then that, yeah, well, maybe that is sufficient to warm us up to the topic of calibration. Unless you have another question you want to ask.
Is there a remote that you can display?
Yeah.
Okay, so that was actually extremely interesting. So I don't know, as a rough guess, Like half of the people here really want to do calibration. Some of you want to use your tools to improve calibration. Some of you want to know something more about the use of data and how you can use different kinds of data and what kinds of data are necessary. And in the discussion, it will be extremely interesting to come back to all of these points. So what I'm going to do now is just a short presentation of what the AgMIP calibration protocol is, and then we can, based on that, continue the discussion. So I could see this. Oh, okay. So these are the questions that the AgMIP asked because we have to fill out the slides at the end of the working session. So what are the existing AgMIP and related activities in this area? Well, of course, the one major activity is the AgMIP calibration group, but I think the other related activity is a lot of people in AgMIP. I think everybody who is using models is also doing calibration. So that's definitely related work related to calibration. What are the most recent advances? Well, that's what I'm going to describe in a second, which is this AgMIP calibration protocol that we've developed. And software which can partially automate the application of the protocol, and we're working on making it totally automatic. Okay, I don't want to go into a lot of detail in the history. The whole point of presenting this slide is simply to convince you that this is not a protocol that we just built on our own in the last year or so. This is a project that has been going on for 8 or 9 years. We started by looking at what modelers actually do. So these are studies where we did multi-model studies and asked the modelers participated to give a lot of detail of how they did the calibration, to give us an idea of what is the range of possibilities, what are people doing in calibration, because we thought we should build any calibration protocol on what the current practices are. We analyzed that. We saw that there were very, very large differences between the different calibration between the different modeling groups. And I'll give you some numbers about that in a second. So based on all of that, we built a protocol just for phenology data because we thought it was worthwhile starting with a simpler problem before going to the general problem of calibrating crop models. So we proposed this calibration protocol, which is to a large extent is based on what people do, but as I'll show you in a minute, also has innovations that are not included in the range of things that people normally do. And I'll explain why we did that. And then we did a study to compare structure and parameter uncertainty in models. I'll show you just a brief result of that in a second. And based on all that, we proposed a general protocol. That's what I'll be talking about today. A general protocol that is supposed to be applicable to any model, to any data set. Certainly will turn out not to be exactly true, but we hope it's more or less true. And we tested that on both artificial data examples to make sure that we know what the results are. And then we tested it on a specific model. And we now have a multi-model study underway to apply this protocol. Okay, so this is the results. One of the results from when we were focusing just on phenology, and what you're seeing here is predictions of days to I don't remember what, maybe I don't know, maybe heading, and each one of these is a model. So each one of these vertical lines is a model, and the triangle and the dot here are every group did first the calibration in whatever way they usually do. So this is the usual calibration approach. And then this is with the proposed calibration approach the proposed protocol that we proposed for phonology data. So we were taking this as two reasonable ways of doing calibration for the same model. So the two ways are the usual way and the protocol, and what you see here are the large differences between different reasonable, acceptable ways of doing calibration for the same model, and you can analyze these with an analysis of variance to see how much of the overall variability between models. When you look at if you imagine this as a multi-model study, so either using the usual method or using the protocol method, how much of this variability is due to parameter differences, to calibration differences, and how much of this variability is due to structural differences. And when you do the analysis of variance, what you find is that 69% of the variability comes from the calibration, and 31% comes from the differences between models. So this is an indication, I mean, it's case study. It's actually a couple of different case studies. This is an average over 2 case studies, but this is a strong indication that calibration has a really, really strong effect on your results. Okay, so what I'm going to do now is very briefly go through the protocol that we're proposing. This is a protocol that has 9 steps, step by step. It's a protocol that is built to lead you hand by hand through the calibration process. So the first step is define the default parameter values. Everybody does that. You don't have any choice but to do that. We include it in the protocol because we think it merits a bit more attention than people usually give it, because most of the parameters are going to stay at their default values. So the default values are important. And secondly, when you're going to estimate parameters, you're going to start the estimation, the numerical estimation, from the default values. So you want reasonably good default values. So you want to think about these a bit. List the observed variables and the simulated equivalents. And also, obviously, that you're going to do that, you have a list of what is the data that you have available, and what are the equivalents that are simulated by the model. And the recommendation of the protocol here is to use all of the possible data. We think it is important to use as much data as possible. The more types of variable you use, the more processes in the model you are adjusting to data, and probably get a better overall representation of the functioning of the system when you use as much data as possible, as many variables as possible. So the idea here is, if you have it in the model, you're going to use it for the calibration. Define the order of variable groups for calibration. So we're going to go through the variable groups variable by variable. So first of all, we're going to group the variables together. All of the phonology variables are going to go together. So if you have days to different development stages, those are all going to be treated together. If you have multiple biomass measurements over time, those are all going to be treated together, and everything else is going to be in a group by itself. Essentially, this is, for the most part, anything that has different units is going to be in the group by itself. And defining the order is extremely important. This is very common practice in calibration. Cloud models calibrate not using all of that data at the same time, but using one or a few variables at a time, because that allows you to reduce the number of parameters that you're estimating simultaneously. We'll see that that's we don't have quite the same problem with the protocol, but nonetheless, we don't want to treat the whole system together. And so we're going to do this variable by variable, but the order of the variables is extremely important. You want to order the variables in such a way that when you estimate the parameters for one variable, you don't want that to change the fit to the variables that you treated before. Almost always, the first variable group will be phenology, because estimating parameters that change phenology are going to change everything else, the simulations of all the other variables. On the other hand, changing parameters for yield, for instance, often have, in general, have zero effect on phenology. So phenology is the first variable group, but the other variable groups, it depends on the way the model is structured. This might not be so easy to determine what is the best order, and we have a diagnostic that I talk about briefly at the end, which tells you whether you made a good choice of the order or not. For each variable or variable group, you want to identify one bias reducing parameter. What is a bias reducing parameter? We know that in a model, linear model or a nonlinear model, if there's a constant term, estimating that constant term automatically eliminates totally bias. That's extremely useful because with one parameter, you can eliminate bias, and bias is often a very large part of the total mean squared error. So this is, I call this the bias removal, the low-hanging fruit of calibration. Of course, crop models don't have additive constants, but they often have a parameter that has more or less the same effect in all environments. And any parameter that has more or less the same effect in all environments is acting more or less like a constant, and it's going to more or less eliminate bias. So you want to identify a bias reducing parameter for each variable, and the allowed number here is exactly no more than one bias reducing parameter per variable. You can only have one constant in your model. Okay, so the next step is to identify additional parameters. So in general, eliminating bias is not sufficient. You want a model that not only is on the average gives you the same results as the observed values, you also want a model that tracks the differences between different environments. You think that there are other parameters in the model that are going to allow you to do that. And so here you're going to list these parameters that you think are the most likely candidates to explain the variability between its different environments. There is no strict limit on the number here. You can have as many as you want. We're going to test them. And we're certainly not going to estimate all of them. We're going to test them to see if we want to include estimation of those parameters in the calibration or not. Okay, once you've done that, we've gone through a large part of the protocol already. Normally, you should, if you really are familiar with your model and your data, this should take, an hour. We're talking about a very short period of time. You are essentially, when you've gone through these steps, you've done the translation between the general recommendations of the protocol and the specificities of the data set and the model you're working with. Based on all of that, these are the steps that require model expertise. Once you finish these steps, we don't require any more model expertise, and the rest is calculations. And the calculations can be automated once you have all of this information. So that's what we've done in our case study so far. I said before, we don't yet have a tool that is completely general for doing the calculations based on this information, but we hope to have that in the not too distant future. So we finished explaining it, finished using model expertise to decide what the translation of the model and data is to the protocol. Now we're going to do the calculations. Okay. Going to do the calculations. First, we're going to go through the variables step by step in the order that was determined here. Okay. And at each step, we're going to do this. First, we're going to estimate the bias reducing parameter automatically. That's automatically included in the calibration. And then we're going to go through the candidate parameters one by one in a type of forward regression. And for each one, we're going to fit this parameter plus whatever previous parameters we already chose. We're going to fit those parameters to the model. We're going to look at how well the sum of squared errors after having done that. And based on that, we're going to calculate a criterion, which is called the corrected Akaike information criterion. What? There it is, which is for those who are used to these kinds of terms, it's a penalized likelihood. What it is it depends on the sum of squared errors, but it's got a period, so the smaller small sum of squared errors, the better. But this includes also a penalization term, which increases as the number of parameters increases. So what this does is it makes sure that you only accept the candidate parameter to be estimated if it reduces this criterion, that is, if it reduces the sum of squared errors enough so that this penalized criterion is reduced. This is very similar to statistical model selection. The selection here is between, do I estimate a parameter or do I not estimate it? And an important point here is AICC criterion is one of its properties is to avoid overfitting. So if you just decided on the basis of sum of squared errors whether to estimate a parameter or not, you would include all of the parameters in your list. But using the AICC criterion guards you from having overestimation. So overfitting, that is, it more or less assures that the errors in prediction are similar to the errors in fitting the model. And when we've looked at this with very rigorous tests of prediction error, we see that this works the way it's supposed to work. Okay, so once we've done this, we've done what modelers mostly do, except that we've added this AICC criterion to avoid overfitting, which I think is totally original compared to what is done normally for calibration. And the other major innovation in this calibration protocol is this step 7, which is the problem is once we've done step 6, we have parameters that have allowed us to fit each one of the variables individually. At the end of this procedure, it's not clear that we have the overall best values of the parameters, because it could be, first of all, that there is some feedback, and so estimating parameters in this list of parameters may have changed the fit to previous variables. So that might not, the fit to previous variables might not be optimal. And also simply, it might be worthwhile changing the fit to some variable to improve the fit to other variables. But we know how to take into account multiple variables. In statistics, we do that with weighted least squares. The standard method of weighted least squares is you get a first approximation to the parameters. You use that to estimate the weights, and the weights are 1 over the standard deviation of model error. So you have an estimation of the weights, and you use those weights to do weighted least squares, where you treat all the variables at the same time and all of the parameters at the same time. So we have this weighted least squares step. We use this as our first approximation until the parameters. We do the simulation. We look at the errors for each variable. Based on those errors, we can calculate the correct weights for the weighted least squares step, and we do this weighted least squares. So that's the end of those are the two calculation steps. And then the two remaining steps are, first of all, we have diagnostics to test how good your decisions were. So there are two kinds of diagnostics. One diagnostic, how good was your choice of the order of variables, and the other diagnostic is how good was your choice of bias reducing parameter. And then our last step is evaluation of goodness of fit and evaluation of prediction accuracy. There's nothing new here. Standard methods are the methods that you can apply. Okay, this is very quickly just some examples of the tables. So the protocol includes definitions of tables you should be filling out as you go through the protocol. This is the table. I won't show you all of these tables. This is the table with bias reducing parameters. So in this particular case study, there were 3 phenology variables. So there are 3 bias reducing parameters. There are 2 bias producing parameters for biomass and 1 bias producing parameter for the groups. These are the candidate parameters, are just to show you make the list of candidate parameters. This is the results of doing the calculation. So you have the table at the end is for each one of the parameters. This is a list that includes, of course, all of the bias reducing parameters and the candidate parameters that were chosen for calibration. The other candidate parameters are returned to their default values, and this is the table that shows you the results on that. And this is one of the diagnostics. This is the diagnostic on bias reduction, and this is one of the diagnostics here is simply to look at how important is bias. Is reducing bias really useful for in the calibration? And so this is the fraction of mean squared error that is due to bias for the different parameters. So in fact, in this particular case, using the default values, 92% or over 90% of the mean squared error was due to bias. Reducing bias is really important, really useful to have this bias reducing parameter. The other values are variable, but on almost all cases, reducing bias is really important. And this is simply the final one of the evaluation graphs. So you can have a lot of these, and then when you normally would have a lot of these, this is how well the model fits the data after the end of the protocol. And what we've seen so far systematically but this is with one specific data set, is that the model after calibration fits phenology very well, fits biomass quite well, fits grain number reasonably well, and does terribly for anything related to nitrogen, and is not really great for yield. That's we can discuss that. Okay, so why would you want to use this protocol? Well, it's user friendly, so it walks you through the calibration process step by step, and it has standardized documentation, which is useful for the person who's doing the calibration. But also, if you're collaborating within a group, it's a very convenient way of sharing information about what you're doing. And when you publish this also gives you a good way of presenting what exactly you've done. it's based on standard statistical regression methods. So we know it's built to avoid overfitting, and what we've seen is it really does that. It uses a statistically optimum combination of weights for the different variables in this last weighted least square step. And so we think that one of the arguments in favor of this calibration protocol is it has a very solid statistical basis, which we think should give confidence in the usefulness of the protocol. It is designed, I said this, to use all the data. So there's no particular, there's more computing time, but there's no particular difficulty to add extra variables. And we think that's really important because we want to use as many variables as possible in the calibration in order to get a better fit to as many processes as possible in the model. It includes diagnostics, so not only do you run the protocol, but at the end of running the protocol, you can at least look at some of the decisions that you've made and see whether they seem to be confirmed by the results or not. So what we say is choice of bias reducing parameter. Diagnostics will tell you whether you made good choices or not, and the order of fitting the variables, the diagnostics will also tell you whether there are problems there or not. It's generic, that is, it's built, it's not, as you've seen, there's nothing model specific about definition of the protocol. It is meant to apply to essentially all models and all data sets, and that has a number of implications. One is, first of all, that's convenient. So if you learn one calibration protocol, you can use it for a lot of different cases. And also, a lot of a lot of comparison studies that we want to do. And a lot of these comparison studies, you can't do them unless you have a standardized calibration approach. Well, let's look at, for instance, just multi-model comparison studies. And what you're doing is you're comparing differences in model structures, but also differences in the calibration. So you can get much more interesting comparisons between models if you have a standardized calibration approach. So that's one thing. There are questions about what is the minimum data set? How much data do you need? We don't, I'm not sure that that's the best way to formulate the question. Question is, how does prediction accuracy change with the data set? Adding more data, more environments, how does that improve my prediction accuracy? Or am I better off, instead of investing in more environments, investing in measuring more variables? How does that affect prediction accuracy? You can't answer those questions unless you have a standardized way of using the data that you're talking about. So having a calibration protocol allows you to start answering questions like, how does the quality of prediction depend on the amount of data and the type of data that I have? And another reason that you need a standardized protocol is for cross calibration. If you want to test prediction accuracy by cross calibration, you have to, for every different split of the data, you have to do the calibration in the same way. So you need a standardized calibration approach to doing that. But so the goal of the calibration protocol is to use the available data in the best possible way, to do the best you can with the data that you have. There is no guarantee. This is the small print at the bottom of the protocol package, and it says there is no guarantee whatsoever that you will get a good fit to the data or good predictions. That depends on your model and on the amount of data you have. So that's where we're at now. What are the next steps? And this is one of the subjects we're going to discuss. What you think the next step should be. So in the development, one is getting to the stage where we have software that completely automates the use of the application of the protocol and tests with other data and other models and other crops. We have been fairly expensive for us, but with one specific data set. So it's really important for us to see what's going to happen when we start looking at other data. The second dimension of these next steps is diffusion. Somebody yesterday said that there's no innovation without adoption. So you're not really interested. Well, I'm also interested in publishing papers about the calibration protocol, but the real goal is to have it used by modelers. And so we're very interested in calibrating with collaborating with other AgMIP groups. And the other aspects of diffusion, we could imagine maybe an online webinar at some point to explain the protocol and answer questions, or a web page which could keep up to date with modifications and information about the software. So this is the list of questions on the official AgMIP questions that we're supposed to ask at the end of working session, in the last part of the working session. These are the questions I would like to ask. So for us, for the calibration group, so AgMIP insists a lot about interaction with stakeholders. Well, here we are interacting with stakeholders because the stakeholders of the calibration group are the modelers in AgMIP. You are our stakeholders. So we are maybe the only group that has a large number of stakeholders present here at AgMIP10, and we're interacting with you. So it's up to you to tell us what you want, what you need, or maybe a easier question to answer is what would convince you, what qualities, what properties, what additional information tools would convince you to use this protocol. So we're, and I don't know, you want to add some more questions to that?
Maybe we should ask for questions to the talk first.
Thanks for the presentation, and I totally agree with that. The data selection is very important for the calibration, and I noticed that in the GGCMI phase 1, like the different models, like they use like different, like maybe most of the set-based models, I think they use the set-specific calibration, and very few like models use I think the gradient style data to calibrate it. So I'm wondering like if you can provide some comments on those two data selections, because I think the ground truth data, the experimental data, they are more accurate, but the graded cell data, they can cover the diversity of the the soil, the climate across a large region. And I'm wondering which data selection you think is the most appropriate for the overall global simulation. Thanks.
Okay, so yes, so as I understand it, there aren't really two choices here, because if you're doing pretty global studies, that's the data that you have.
Yeah.
Okay, and so it seems to me the underlying question is, how do you calibrate using that data, given that it's multiple different varieties, or you have separated this data into separate varieties or variety groups? So, sorry, maybe the underlying question is, how much is it worthwhile to pool the data or not? How that, to what extent, if you have data from multiple different situations which are not the same, these are all assuming that there are parameters depend on variety. So, assumption I think behind co-op models is that different varieties will have different parameters. So if it were possible, if you had enough data, you would like to do a calibration for each variety separately. Question is, when you have varieties, when you're pooling varieties, you have varieties that are similar. Should you pool those, put those together because it gives you more data, or should you treat them separately because you think the parameters are not exactly the same? And you can, with this pooling, you can extend this to varieties that are more and more different, going up to global scale where you're treating all of the data together. So is it worthwhile pooling that, or is it worthwhile separating it into groups? Is that a reasonable I've totally reformulated your question.
So I understand that way. So like the crop variety is a variety you're talking about, that crop variety. It's like so maybe the climate gradients or the environmental gradients difference are not that kind of important to calibration, but the crop variety is the most like important variable to identify the questions. Yeah.
And so I don't know. All I can say is, if you have a good calibration method, then you can test this kind of thing. And one of the things I didn't say is it is really interesting to use artificial data for testing questions like, how should I be treating all varieties together or separately? And that will determine how much data I have. Those are questions that you could answer with artificial data. And so I'm not a huge fan of artificial data because it's artificial, but there are some questions that really, that's the way to get answers, I think.
Thank you.
Yeah.
Thank you so much for the nice presentation. We're currently try to calibrate our models with respect to intercropping system that is highly dynamic and complex. And we assume to calibrate the models, like we use the sol crop as a default for the calibration, like each group to calibrate the models using the sol crop information as accurately as possible. But from the presentation I saw here, we are emphasizing the variability in the calibration approach plays significant role, far better than the model structures. So what is your view? How do you think the best approach so that we can calibrate our model to minimize uncertainties or to make better in the comparison?
So sorry, can you give a concrete example of what you would like to do?
For example, now we want to test how each model assumptions represent live competition. So we have, like, for example, 6 different modeling approaches, and each model differs structurally and differs based on number of parameters to represent the competition. Then we are thinking of providing data sets that's common across all the models. Then we say that let's use sol crop, because sol crop, all the models was assumed better in simulating sol crops species. Then each modeler will calibrate the model using the sol crop data. Then the evaluation will be done with the intercropping. So I just want to know, like, how best way can we move ahead?
Okay, so that's maybe 2 questions, and I wouldn't even try to answer the second. The first one is that the best way to do the intercomparison for a single crop and then a question which I could leave to others is how to handle intercropping. The problem of a multi-model comparison for a single crop is a very standard question that a lot of the different AgMIP groups are asking. And yes, and what we've seen is this huge variability between the different modeling groups. And yes, I think that this would be extremely useful to ask people to use the same calibration protocol. Everybody uses a standard calibration protocol. What we've seen is that is definitely going to reduce the variability between different crop models. And because that's what I said right at the beginning, a lot of the variability that we see in simulations is not due to structure, it is due to parameters and in particular to calibration. So imposing a calibration method is a good way to reduce variability in these intermodel studies. And therefore to allow them to better analyze the differences in terms of differences in structure.
Nice. So for example, do you suggest that we can adopt this protocol as a baseline for the intercropping?
And then, but are you recalibrating the model for intercropping?
Yeah, the first stage, we test how the models response with salt, the default salt probe calibration. Then, as we have pointed out in this initial round, in the second round, we now test if we provide additional information, additional data set from the intercropping experiment, and how does that improve the calibration accuracy? Is another question.
Okay. So I have no experience with applying the protocol in intercropping. I don't think my first impression would be that yes, that should be possible because there's nothing here that, I mean, what we're doing here is we're using observed data versus simulated data. And whether this observed data is data for separate, for two different crops in intercropping, or whether it's from a single crop, I think the calibration protocol would work exactly in the same way. But so it would be interesting to look at, but I think you could apply the protocol to intercropping as well. And if so, it is worthwhile because I mean, not only is there is a lot of diversity in calibration approaches, but what that also means is that some of those calibration approaches are really not very good. Let's face it, you can't have a large variability like this and have everybody being right. So it is worthwhile having standardized, reliable, more or less reliable calibration approaches to calculate the better.
Leonard, I've seen you, but for laziness of my own, I have a simple question. Thanks for the clear presentation down there. You explained that you removed the bias introducing parameters in the process, but when you showed the results, some of the variables seem to still have the bias in the prediction and not in the fitting after you fitted the data. How can that happen?
Yes. Okay. So yes, you're absolutely right. I thought I went through those slides, graphs fast enough so that nobody would notice that. So crop models don't have additive parameters. They have things that have more or less the same effect in every environment. And so I'm not totally sure that applies for every variable in every model. And you have to, but even if it does, then the person who is doing the calibration has to correctly identify that bias reducing parameter. In this particular case, so we applied these we asked the modeling group to to follow the protocol. At the end, we looked at the results and we looked at the diagnostics, and in particular the diagnostics related to bias reduction. And what we found is the diagnostic related to bias reduction is extremely simple. You simply look at how much bias there is before you estimate the bias reducing parameter and how much bias there is after estimating the bias reduction parameter. So there's no secret, and it's very easy to see. And what we saw were two things, two of the variables have problems. The nitrogen content of yield, estimating the bias reducing parameter, had no effect on bias. So the conclusion is that is not a good choice of bias reduction parameter because it doesn't reduce bias. And the group said they didn't see a better choice. And so the idea there would be to rerun the protocol without that, with no bias reducing parameter in that case. And the second variable that was interesting when looking at the diagnostic was yield. When you estimated bias before the bias reducing parameter yield and then right after, that bias reducing parameter had essentially no effect on bias, but there was a candidate parameter that was accepted, and the bias after the candidate parameter was very small. So in fact, it was the candidate parameter that should have been a bias reducing parameter and vice versa. But you can see that very clearly from the results. And so in rerunning the calibration, they will need to inverse the candidate and bias reducing parameter for yield.
In the interest of time, if we want to go to these questions and go through the questions that you have, let's have questions and answers very short.
Okay.
Yeah, I wanted not to ask, but answer two of these questions. What I want, you said you want to develop a software. I thought we had one that was kind of model agnostic in Croptimizer already. Is that building on it or trying to reinvent the wheel more or less?
Okay, so yes, thank you. I mean, I kind of felt I should put this in, but yes, we hope that what you need is the calibration protocol with the associated software.
So new one.
No, not a new one. No, we're not going to start over again.
It would be integrated to me. Actually, I'm working on AgMIP10 calibration protocol phase 3 was integrated already. And now, so for the exercise, we developed some scripts based on this optimizer package to run the protocol on our particular data set so that participants can run it easily. Then now the full phase 4 protocol will be fully integrated into Optimizer. So I started the work. The multi-step phase, the beginning, so multi-step parameter selection is almost already implemented. So hopefully, let's say in 1 month or 2 months, it should be really run. So the idea would be that we have a software that automates this phase 4 protocol, and so that it can be applicable on any data set and any model connected to the software. And so in the past exercises, it has been connected with around 12 or 13 models.
One click and just let it run for free. See if you have a model which is connected to it.
Concept for the traffic way.
So I'm not sure if I missed it right in the beginning, but before you go to grouping the variables, do you also have a step where you decide which parameters you want to calibrate? Like maybe and I recognize that every model, not all models have same parameters, and the set of parameters, number of parameters differ in different models, but is there a guideline that people can follow on which parameters to calibrate and which ones do you not want to touch maybe?
Yeah, okay, so I hope that was clear that there is the choice of parameters to estimate is first bias reducing parameter for each variable, and then
In overall, so even even before that. So there are like lots of parameters, like hundreds of parameters. Are you considering all of them and grouping them, or so there are hundreds of parameters in a complex crop model.
Yeah.
So are you considering all of them, or are you just looking at a subset?
Well, so like once again, the subset is a bias reducing parameter and a fairly limited list of candidate parameters.
So that limited list of candidate parameters, how does one?
Okay.
Okay.
So that is a very important choice related to the model and the data set. For instance, if the data set, in the case we had, was essentially all of the data came from environments with the same photo period. So adding a photo period sensitivity parameter doesn't seem like a really useful thing to do. So the choice of parameters can depend on the data set and of course on the model. What we would like to see is recommendations model by model for what parameters are probably the most important. This is a hard decision. It's hard for every user to make this decision. You have to really know how the model is built and what's going on in the model. And to choose this bias reducing parameter, you really have to understand what these parameters, what function they're playing in the model. So this requires quite a bit of model expertise. We think that it would be extremely useful if DSAT, APSIM, STIX, whatever, Wolfhost would have recommendations for what they think are the most important parameters. And the bias reducing parameters and most important parameters for different types of situations. But that's a real problem.
My name is Santiago. I work more with a crop development, so maybe my question don't make sense. About the synthetic data, do you think it's a good idea? For instance, if I have a ranking of the models and the model is ranked as the first, it's a very good model relating to the others, and I'm kind of in the last part. Do you think it would be a good idea to using these models to generate a simulation and try to use that as a synthetic data to calibrate my core model? This is the first question. And the second one, sometimes we see that in the calibration to try to reduce the bias and ultimate square error, sometimes the model lost the sensitivity, try to go to the average, because they are not good to predict spatial temporal variability. So then the parameters are very bad. So there is a way, and as a user, I prefer a model with a bias, but predicting variability. That is what most interesting. How? So these are the two questions.
Okay, I think the whole idea of ranking models and giving this is the best model, this is the second best model. All our experience is that it depends on the situations, and some models are better in some situations, some models are better in others. So probably the idea of having this ranking is probably not a good way to go. Using artificial data to do it is not a good idea, because you have to generate the artificial data. What we do is and how do you generate artificial data? You use a model. So if you use artificial data to rank models, what you would really be ranking is how close are they to the model that you chose to generate your artificial data. And probably so I would say don't do that. Yes, remind me of the second question.
With the spies, but you lose the variability. The model starts sending to the.
So yeah, whether the problem if you so yes, if you just removed bias, that's probably in most cases In a lot of cases, that's all you can do, but you certainly want to look at other other parameters to reduce also the variability between environments. This protocol does that automatically. It does eliminate as far as possible bias, and does also search for parameters that explain the variability between environments. But
Thank you. Shall we move on? Sorry. Thank you, Daniel. I wanted to ask you about how the calibration is linked to validation. Do you think that part of the calibration protocol needs to be a validation step?
Okay.
By having a holdout or do a cross validation, because there is a bias also in the data you have available. Yeah.
Yeah. Okay. Now that is a really important question. And in very general, how do you do evaluation, and then where does the protocol fit into this evaluation? But I think the question of evaluation is larger.
I was mostly motivated by a discussion we had yesterday that someone mentioned in the machine learning workshop that we use a machine learning model, which is a very flexible model. And then you have an R square of almost 1. Then it memorizes all your data, and it's great. But then it has no capacity to generalize anywhere, right?
Yes.
And that's not possible with a crop model, but
you have almost the same problem with crop models. You can always add more and more, estimate more and more parameters, and get closer and closer to a perfect fit to the data. It's extremely important that the protocol avoids that by using this AICC criterion. I think it really depends. In this particular case, all of the case studies we've done so far, we have split the data. We've done data splitting.
Okay.
And not only did we do data splitting, but we made sure that the evaluation data was from different years and different sites than the calibration data, to make sure that we were really evaluating how well the model predicts out of sample. I think in a lot of cases.
That's my question, but then because that was not part of the protocol very explicitly.
No, but that's not part of the protocol. It depends on whether you have enough data to do that. If you don't, you might want at least to do cross-validation. And for cross-validation, the protocol, like I said, is essential, because if you don't have a standardized way of doing the calibration, you can't compare the different ways of the results from different ways of splitting the data.
Yeah. Yeah, about having different sites for, I think you introduced an uncertainty due to the solid. Yeah, because quite often we don't have enough data to really well characterize the solid. But that was just a point. That was not my question. My question is, do you think it could be a bit dangerous to select just one parameter that has large linear effect, or close to linear, I guess, like relative efficiency or time and time? Because then you transform your complex model into a multilinear model in a way. And another thing is, then the risk is that you modify parameters that should not be modified, or that they are out of the range. For example, if I see the radiation efficiency you have there, I don't know if it's based on radiation in PAR or global radiation, but if it's in PAR, 4.3 for width, I don't really believe it. So my question is, do you think it would be useful to have a step where you actually estimate the parameter? Like, there's not that many data sets where you have good estimation of reliable estimation of radiation efficiency, but they exist. Then you can see if you get to make that sensible, because you can underestimate the Lifari index and then you overestimate the radiation efficiency and strict.
Okay.
So how do you guarantee that the value you get are kind of the true value or close to a true value, and you're not making a statistical model at the end?
Yeah, okay. I'll start with that because, okay, that is an interesting question, which is both philosophical and practical. That is, what do we think these parameters represent? So I said that this before for us, for the protocol, the idea of the underlying theory is that the parameters are not constants of nature. So the best there is the only thing you can say is now our best parameters for each target population. Given a target population, there are values of the parameters that give you the best predictions based on that data. And these are not, if you go to a different target population, you will get different values of the parameters. However, that crop models are not simply very complex regression models. They also represent real processes, and these parameters represent real things that are happening. And so the underlying philosophy is that, yes, the best parameters differ from target population to target population, but they don't differ that much. They have to be in some range, because if they go outside of this range, you get really absurd behavior, which is going to give you absurd predictions somewhere. So the idea is what we have here are limits, upper and lower limits for each parameter, which represent what we think are reasonable values for these parameters.
Yeah. But it would be interesting to you can get a data set, I think, where you can have estimated value from the measurements for pretty much all your bias correction parameters.
Sorry, do that again?
I would think that you can find a rich data set in which you can estimate most of all the bias correction parameters, like radiation use efficiency, fusing efficiency, thermal time to release boost state, vernalization.
But that's the value in a model is under some optimal conditions. You will only get to that with optimization.
Yeah, I don't think those will be the same parameters that you want for a particular target population. They're very interesting as starting values, as default values, and I think you want to allow them to be adjusted to the data, because I don't think that those are exactly the same values. Radiation use efficiency is not a constant of nature. It depends on the row spacing. It depends on the row orientation. I remember that study on this years and years ago, looking at how that depends on row orientation. These are not
a bit. You don't have value of 4.3.
Let's park that from the discussion to the coffee break, which is just less than 10 minutes. So you just hold it back for a while. Maybe to wrap it up. So what do you want besides climate justice is obviously a hotline for a consultation on your own calibration effort. And Daniel will share his phone number afterwards.
Yeah. Yes.
But maybe also to get a sense of, like, everyone's here is enthusiastic about calibration. We asked that in the beginning. So who of you would be doing a calibration in the coming 12 months, giving Daniel's protocol a try? There you go. You can change constitution about it.
And get in touch either with me or one of the leaders of that. Yeah. If you want to do this, please get in touch with myself or one of the other leaders of the calibration group, because we are extremely happy to see people apply the calibration protocol, but we also would like to make sure that it's being applied correctly.
Yeah, also please send an email to the group. Please send an email to the group so that we can keep you updated about the software, those who want to test it, to test the protocols.
This software, it's a package or?
Yeah.
Okay. So it's not really.
Anything we missed on what you want, what you need for calibration to make your life easier or happier?
I have a very big problem with the comments I've heard about calibration for current conditions. A lot of talks here have been about how they are applying these impact models, drop models for the future climate scenarios. There were people talking about benchmarking the data that we have right now, and we know from the discussions here that we have lots of varieties. I'm lost. I'm really lost. So all the calibrations that have been done and being applied to climate change models, are they useless? Comments, please.
Okay, so that is also a very large question, which is the relationship. You have data from a certain set of environments that you use for calibration, and then you use the model to predict for other environments. The assumption here is that you're using it to predict for other environments from the same target population, that is, that have more or less similar to the environments that gave you the calibration data. What do you do? But in a lot of cases, what you want to do is apply the model in very different situations. What can you do in that case? So first of all, extrapolation. Prop models are no exception to the very, very general rule of prediction, which is extrapolation is extremely dangerous. If you didn't, for instance, if you didn't have any data on the effects of CO2 in your calibration data, you don't know anything about how well the model is going to predict for higher CO2 levels. And that's why in most cases, in most of the AgMIP studies, people use face data or other data with enhanced CO2 to make sure that the model is correctly reproducing the effects of that. So yeah, you don't want to predict for things that you have never seen and calibrate with data that has no variability related to the variability that you want.
Yeah, that also alludes to the question, like, or the difference between the projection and the prediction. And I guess that's also good to keep in mind. What we are doing when we are applying drop models for future conditions, which is the projection and not prediction. And that we need to keep in mind in the interpretation of what we see. Right? Like that's maybe that would be another AgMIP10 workshop on the philosophy and the sensibility of using models in the first place. Yeah. Thanks so much, Daniel. Maybe a big hand. He didn't pull off the presentation all by himself, but also this calibration exercise wouldn't exist without you. So thanks so much. And if there are no urgent, this is what we need from calibration voices left, I would say thank you all for being here in a lively discussion, and let's see you at coffee.
And I also thank you.
I should call you. I will say I can't walk on the phase one.
Sorry.
Yeah,